All right, guys, so in our last video, we were talking about how to decide whether or not you're dealing with a one-tailed test or a two-tailed test, where pretty much a two-tailed test was more of a yes-no binary consideration. Does it equal this number or does it not equal this number? So that's why when we have our standard setup for a two-tailed test, we have the population variable, whether you're dealing with the mean or the proportion. Make sure you're using the appropriate population variable, either equals the number that's in question, or it does not equal the number in question. It either is or it isn't. When we're dealing with a one-tailed test, we're considering one direction only. So we're interested in if something's greater than something, if it's less than something, if it increased, decreased, improved, worsened. Those are the keywords you need to look for to identify that, in which case we're dealing with either a greater than or a less than, and it always has the equal to in that null hypothesis, or the greater than or less than in the alternative hypothesis, and those are just going to be the opposite of one another. So we're going to go through a couple of problems now, and I'll have those problems in the description for us to just walk through. They're going to have a lot of details, and they could ask you a lot of different things, but in this situation, we're just going to identify whether or not it's a one-tailed test or a two-tailed test, and how to set up that hypothesis. So we're going to go ahead and start with the, one example where we have the average U.S. household has $235,600 in life insurance, so that's just other information we're not really going to need right now. But it goes on to tell us that a local insurance agent would like to see how households in his city compare to the national average. So let's stop right there because we have all the information we need to figure out how we're actually going to set up this hypothesis test as far as whether or not it's a one-tailed test or a two-tailed test. So let's just go ahead and set up our null and our alternative hypothesis right here. Okay, and we're always going to put in some population variable first, right? So it's just going to be whether or not it's a mean or a proportion. In this situation, we're talking the average U.S. household has $235,600 in life insurance. They say the word average, the number they're giving you is a specific mean value. We're talking about a mean-based problem here. They're not talking about a part out of a whole, some percentage of people whose life insurance is above a certain amount. It's nothing like that. We're just talking about a specific number here. So we're definitely going to be talking about mu, which is the population mean. So we always hypothesize about a population, okay? So that's how you start off right there. So that takes care of the population variable part of it. And we have to just here decide whether or not it's a one-tailed test or a two-tailed test. Well, what they're asking is the local insurance agent would like to see how households in his city compare to the national average. So first of all, the national average, that number that we're wondering about, is going to be that 235,600, right? 235,600, because that's what we're speculating about. We're speculating about that population value, and we're just going to use sample information to be able to speculate about it and accept or reject the hypothesis accordingly. And we'll get to that later. But just to set it up for right now, if we're wondering how does it compare, that's a really general statement, right? They don't say, is it greater than, is it less than? If they were specifically wondering about that, they would have told us that. But here they're just wondering, how does it compare? That tells me they're wondering, is it the same as the national average, or is it not the same as the national average? So does it equal the average, or does it not equal the average? So in that case, it's going to be a two-tailed test, okay? And so as you continue through the rest of the problem, which we'll get into in future videos on actually how to solve for and accept or reject a hypothesis, this is just going to be the setup for it. So that's how we take care of that example. So let's go on to another example we have, where we have the director of admissions at a large university says that 15% of high school juniors to whom she sends university literature eventually apply for admission. So she sends these people, brochures for various colleges, and 15% of those people tend to actually apply for colleges, which seems like a good thing, seems like a good resource to engage in. So a sample of 300 persons to whom materials were sent, 30 students applied for admission. So we conduct a hypothesis test. Should we reject the director's claim is what they're asking. So what the director is claiming, so let's begin to set up our hypothesis again. So obviously we're going to have our null and our alternative hypotheses. And in this situation, they're giving you a couple of hints as to whether or not it's a mean or a proportion-based problem. They say that 15% of high school juniors to whom she sends university literature eventually apply for admission. And then they give you a sample of people that they tested to see how many of them actually do apply for it to kind of test that claim. They say 30 out of those 300 eventually apply. So what they're talking about there is a characteristic we're interested in out of a whole, a part out of a whole. They even tell you a percentage right there. They say that 15% eventually go on to apply for college. So in this case, that's telling me that this is actually going to be a proportion-based problem. So the population variable for a proportion, and I've had different stats classes where slightly different variables are used. Oftentimes, we'll see that as pi is going to be the population proportion. So just make sure whatever your class says, put in the population proportion variable right here. And then what they're wondering is if we should reject the director's claim. Well, the director's claim is that 15% of the high school juniors will apply for it. So the claim relates to that 0.15, that 15% that they say actually applies for college eventually. So just like how here the national average was $235,600 for life insurance, in this case we're talking about the average of the population. In this situation, it's just the juniors who apply for college and just the juniors as a whole. And so in this situation, how does it compare? Should we reject the director's claim? Well, the claim is that this number, 15%, apply for college. Okay, well, we're not wondering, is it more than that? Is it less than that? We're just saying, is it that number or is it not that number? Okay, so you don't see any keywords saying, did it increase, did it decrease, is it more, is it less? Odds are it's going to be a two-tailed test. So it's just going to be this standard setup here where we have it either equals it, so we would accept the claim if it equals, or does it not equal 15%, in which case we would reject the claim, okay? So those are two examples of two-tailed tests right there. So let's get into a few more examples. All right, so now we're going to get into the next problem. So what we have here says that in the past, patrons of a cinema complex have spent an average of $5 on popcorn and other snacks with a standard deviation of $1.80. So the amount of these expenditures has been normally distributed. Following an intensive publicity campaign by a local medical society, the mean expenditure for a sample of 18 patrons is found to be $4.20. So in a hypothesis test at the 0.05 level of significance, does this recent experience suggest a decline in spending? Okay, so let's begin to set up that hypothesis again. So we have our null hypothesis and our alternative hypothesis. So whether or not we're dealing with a mean-based problem or a proportion-based problem is the first consideration because we're deciding what our population variable is. And in this situation, they tell you the average spending on popcorn was $5. And then they do the sample, and the average, the mean expenditure of those 18 people was $4.20. Clearly, we're dealing with a mean-based problem here. They don't say anything about a part out of a whole, some percentage we're interested in. It is strictly going to be a mean-based problem. So we have here mu in that situation, because that's the population-based variable for the mean right there. And then what we're comparing that against is always going to be the population-based value, right? Not the sample-based value, because we never hypothesize about a sample. It's always a population. And in this situation, it says, in the past, patrons of a cinema complex, the entire cinema complex, just everyone in the past, have spent an average of $5. And then in the sample, we had $4.20, but in this situation, we're just wondering about $5 right here, okay? And so now we have to decide, is it a one-tailed test or a two-tailed test? Do I do my greater than, less than, or my equal to, not equal to? Well, notice that last sentence right there. It says, does this recent experience suggest a decline in spending? Okay, so we're not talking about the previous problems. We're saying, is it this number or is it not? How does it compare to this specific value? We're wondering, is there a decline in spending? And so if that's the case, remember the way I said that you decide where the greater than goes and where the less than goes when dealing with this? There are kind of two ways to do it. One of them, what you're wondering about, what they're asking about, which in this case is a decline in spending, is what you're going to put in the alternative hypothesis, okay? So if I'm wondering about a decline in spending, that's less than, right? So I'm just going to say less than here, and you just simply flip it for the top part. It's going to be greater than or equal to. Another way you could do that, which is actually the first way I learned it, it's a bit of a kind of a workaround logic way to back into that, but another way to do it is to create conflict with your sample mean, or if it's a proportion problem, your sample proportion. And by that I mean, in this situation, we have $4.20 as our x-bar, as our sample mean, right? Well, if I want to exclude that out of my null hypothesis, which is what you do if you're going to decide to do it this way, if you want to exclude $4.20, well, here's 5, right? So let's draw a little number line here. So we have $5, and that's what we're comparing against, okay? And we have our sample mean is $4.20. Well, if I want to exclude this sample mean from my consideration, I'm going to talk about anything that's greater than 5, right? Because if I said something that's less than 5, that includes my 420, and I don't want to include the 420. I just want to talk about what excludes my sample mean. And in that situation, you could say, oh, well, then it's going to be greater than 5 here, and then you just flip it down there. So you can either decide what we're wondering about is going to be the alternative, or what you exclude the sample mean as is going to be your null hypothesis. So you can kind of check it both ways like that. So that takes care of that example. So we'll get into the next one here, where we're dealing with a manufacturer of electronic kits found that the mean time required for novices to assemble its circuit tester is 3 hours, okay, with a standard deviation of 0.2 hours. A consultant has developed a new instructional booklet intended to reduce the time an inexperienced kit builder will need to assemble the device. So they're hoping that this will help make it a quicker process for you to assemble this device if you're a newcomer and you're not used to doing this. So in the test of effectiveness of the new booklet, so we're running the sample, we have 15 novices require a mean of 2.9 hours to complete the job. So based on the population, it seems like there's probably a decline, like it's taking less time now, so it's improving it. But it says that assuming the population of times is normally distributed and a 0.05 level of significance, should we conclude that the new booklet is effective? Okay, well, here's what would decide whether or not the new booklet is effective. So first of all, let's go ahead and set up our kind of standard formula before we get too ahead of ourselves. So let's talk about, first of all, if it's a mean-based problem or a proportion-based problem. Well, in this case, we're talking about the mean hours, the mean amount of time it takes for you to complete these assemblies using the booklet. So in that case, we're clearly dealing with a mean, so we're going to say mu right here, because that's the population mean, okay? And what we're comparing that to is the population number, the population value. And in that case, that's going to be, let's see, right here, 3 hours, okay? So we're comparing it to 3 hours, okay? So that's what we're used to being the case before this booklet ever came out. So we're hoping this booklet comes out and it's a more effective booklet. So now we're going to decide whether or not it's a one-tailed test or a two-tailed test, and which direction if it's a one-tailed test. Well, in this situation, if a booklet is more effective, that means that it's going to reduce the amount of time it takes for you to complete that assembly, right? Hopefully you're reading the instructions and it's not going to take you more time to do it. That would be very counterproductive and totally defeat the purpose of what the booklet's hoping to do. So to test whether or not it's effective, if I'm wondering, is this booklet effective, that means that it would take less time than it did before. So what I'm wondering about is, does it take less time than it did before? And so that's how you set up your null or your alternative hypothesis. Thus, this is a one-tailed test because we're concerned with one direction only, okay? And with the null hypothesis, you just simply flip it around. And real quick, if we wanted to do it the other method, like I said, where we exclude the sample mean out of the equation when we're doing the null hypothesis, we could simply look at our sample mean was 2.9 hours to complete the job once we had this booklet. Well, if here's my number line, I have 3 hours is what I'm comparing it against, and it says I have 2.9 hours is my sample mean. If I want to exclude that sample mean, I would talk about the stuff that's greater than 3. So if I talked about what was less than 3, it would include the sample mean, and that's not what we want to do. So this would be the greater than for the null hypothesis, and then the alternative hypothesis will be the less than, just because you can flip it around or do by the logic that I first instructed. So that should be several examples to help you figure out how you set up a one-tailed test or a two-tailed test. Like I said, this is very fundamental for you to decide how you're going to continue to go through the problems, because after you set up your hypotheses, there's several more steps you have to do in order to actually accept or reject the hypothesis. But if you don't have the hypothesis set up in the first place, then you're definitely not going to be able to accept or reject accordingly. Your decision is going to be against an incorrectly formatted hypothesis setup. So that's how you set that up. Hope that helps, and just make sure you follow these rules, and you should nail those problems every time.